And for those at the front or with exceptional eyesight, you may have noticed a little red spot there. That area covers about 0.1% of the screen. And what it represents is the entire surface area of the oceans covered by coral reefs. Yet they're heavy hitters in terms of biodiversity. Reefs support between a quarter and a third of all marine species. I can tell you that the ocean would look like a very different place without them. And in anthropogenic terms, they provide sustenance, primary protein source, for hundreds of millions of people around the world. They protect their homes and built infrastructure. And money speaks, so they contribute trillions in terms of tourism and revenue, for example, through medicinal research. Before I go too much into reefs and coral, let's actually take a look at what reefs are built from. And spoilers, I gave it away, coral. Here's a wonderful example of a beautifully colorful organism. An organism which is actually an animal, which lives as a colony of polyps, and which support tiny algae called zooxanthellae, which are harbored within their mineral skeleton. And I'm sure you've all heard of bleaching. This occurs when environmental conditions exceed that which corals find optimal. And in the process, the coral polyp expels the internal algae and exposes that white skeleton beneath. And if conditions don't return to where they should be within a few days or a few weeks, the coral organism then dies off and it becomes outcompeted with this turfing algae. Sadly, these sorts of bleaching events are becoming all but widespread all around the world in reefs everywhere. And a coral ecosystem like this is far less able to support the biodiversity that it would naturally. And of course, that has knock-on effects for the millions who rely on these ecosystem services. So, I'm Orlando. I'm a second-month PhD student at the University of Cambridge. And I'm looking into where coral might be able to exist in the present in order to predict where it might be able to exist in future, so that we can guide and focus our conservation efforts on those regions where coral has optimal chances of survival. The original title of the talk is arguably too wordy, so I'm just going to start by breaking it down. Here we are in the present day with a coral presence map. Also, in the present day, we have some idea of historic environmental conditions which have led to this founding of coral over the last decades and centuries. This, to me, looks like a classic supervised learning problem. We have features, our environmental time series, and we have ground truth label, our coral data. So why not train a classifier? And this is, just as a disclaimer, this is the current stage of the project. Going forward, we're going to look at future forecasted environmental conditions from large-scale Earth system models such as CMEP6. And again, these can act as features to our pre-trained model. And as a result, the idea is for it to output a coral suitability map with hotspots identified for good catch, for where coral will be able to survive into the future. In terms of multimodality, as you might expect, and as we just heard from heterogeneous data sources, they exist from all sources, all types, all resolutions, anything you can think of. My life has basically been trawling through all of these for the last, couple of months. So there are lots of different sources of data, and that's where the multimodal part comes in. Looking at some of the previous work on those data set, we know coral cares about kind of broadly these conditions. However, previous work understands these variables in very coarse spatial and temporal resolutions. And you can see that it hasn't really changed that much in terms of resolution in the last 20 or so years. We're still looking at parameterizations of annual temperatures, annual nutrient levels and things. And in doing so, I'm using similar techniques from previous studies, but using the highest resolution data available to see how things perform. Just to kind of clarify why these coarse resolutions are a problem, Here we have in dark blue the bathymetry, in the red the coral presence, and the part of this white square here is a typical Earth system model grid cell, which might contain average sea surface value or something. To put that in perspective, it's tiny, the coral presence, compared with those variables. So how can you expect to come up with a good prediction of environmental suitability when you're looking at such different scales? In terms of temporal resolutions, this disgusting GIF is monthly, and you can see how jumpy it is and how poorly it captures the actual day-to-day, let alone hourly, variations in those environmental conditions. So for my methodology, I'm using the highest resolution forecasted and historic data from CMIP 6, and it's available at 25 kilometer resolution. Still not great, but the best we're ever going to have, both forecasted and historic. And available at quite a few, quite high temporal resolutions. As I mentioned, to start with, I'm just looking at the historic data, and I've also trimmed down the variables I'm looking just to these key coral predictors, such as temperature, salinity, and currents. In terms of where coral is and isn't, we have some ground truth maps. I've chosen that from the UNEP Coral Atlas, which exists at 30-meter resolution, and depth, which is an incredibly important predictor on the grounds that coral relies on its photosynthesis by its hosted algae. I'm using this globally available bathymetry map at 450-meter resolution. As you can imagine, that's a lot of data to be dealing with. It easily gets into tens of terabytes. And for simplicity and my sanity, I've chosen to focus on a small region on the Great Barrier Reef and parts of Papua New Guinea. I chose here because it has a huge number of different types of reefs, for example, barrier, obviously, and as well as reefs around islands and coral atolls. To deal with this huge class imbalance problem, I've chosen XGBoost, which has basically won every Kaggle competition ever and deals very well with imbalanced data sets. Basically, the way it does that is it iteratively trains the model, and each time increases the sampling frequency of misclassified data points. So it really trains well to those class scarce parts. So I'm surprised this is actually the first confusion matrix we've seen today. As we can see, it performs okay. Not incredibly, but fine. We can see a nice diagonal here, but we can also see that it's still overfitting to coral absence, which perhaps isn't a surprise, even despite XGBoost's kind of best efforts. It's an incredibly imbalanced problem, and always will be. Just think back to that first slide. Yet, in terms of accuracy, again, it doesn't do too badly. Ignore accuracy here, because it's so imbalanced that makes no difference. Decent balanced accuracy, and I'd focus most on the F1 score. I think that's the most realistic depiction of how well it's doing. For context, previous work has an accuracy of 60%. So really, it's doing much better than that using this high resolution data. For a qualitative comparison, we can see, again, it's okay. This is the ground truth on the left, the predictions on the right, and we can see that it's fine, and there's plenty more work to do. And before telling you about that plenty more work, we can see that, as expected, using high resolution data does make a big difference, and I'm happy to answer why this trend stops here if we have time. But increasing the resolution from right to left does increase our scores. And that's really not surprising. This is a little tricky to explain in the time that I have. I shouldn't have spent so long setting up, but we can always come back to it. So I'm a first year PhD, 60 days in. I would love to talk to people who have experience in some of these future options for improving this model. Because at the moment I'm just taking broad parameterizations, monthlies, annual averages, rather than the whole time series, and that's just a waste of data. In addition, there are plenty more environmental variables. Coral cares more about temperature and salinity, for example. There's lots more to look at. And these variables also exist on multiple levels, whereas I've just scraped off the top, kind of the sea surface. And quickly running through this, there are loads of techniques that I want to explore, and if anyone has any experience in them, please do talk to me. For example, increasing the spatiotemporal resolution with various statistical or machine learned methods, various ways to reduce interpolation. Ground truth is a huge issue on the grounds that nobody really agrees where coral is and isn't at the moment, and that's kind of essential in a predictive task. As well as if I'm ever going to do anything with this data, which despite it being a PhD, I really do want to, I'll have to think about uncertainty and explainability. Speaking of what I want to do with that data, I've been exploring the sort of stakeholders so that I can get in touch most quickly with the people who are most involved with the relevant areas. That is a whistle-stop tour of the first couple of months. If we have any time for questions, I'd love to hear them. Otherwise, there will be a notepad at the back, and I'd love people to write anything they think about this at all, any suggestions, contributions. Please get in touch. Thank you.